Hi everyone, I'm Charlie from the University of Leeds and I'd like to present my talk on the influence of surface modifications on powder properties. So my supervisors are Professor Mushtaba Gadiri and Dr. Xiaodong Jia, and I'm sponsored by Malvern Analytical and the EPSRC. So just a quick run through of what I'm going to talk through in this presentation. So we've got glass beads that we've acid washed and then silanized to give us 3 distinct samples. And we've quantitatively measured the powder properties of these samples in terms of their surface charge and their powder flowability. So we induced the charge via something known as aerodynamic dispersion, whilst an FT4 powder rheometer was used to characterize the powder flow. The influence of humidity has also been considered during the charge transfer, and these charge characterization claims are supported by simulation data. So just to give a brief introduction as to what tribo-electric charging is, because it's something that people aren't always familiar with. So it's a form of contact charging where particles become charged via either particle-particle or particle-wall interactions, and they become charged during the collisions themselves. And this can lead to several flowability issues such as segregation, adhesion, and agglomeration. And so contrary, it might be opposing to what you might think is actually, it's not conductors that are an issue, it's actually electrical insulators that are an issue for tribo-electric charging because of their low surface conductivity. It takes a lot longer for that, they retain the charge for a lot longer, whereas a conductor would just simply conduct the charge away. The charge remains on the surface of an insulator for much longer. So therefore, materials with low surface conductivity, such as those found in pharmaceuticals and organic solids, tend to see a lot more issues with tribo-electric charging. So as I mentioned, the issues with pharmaceutical and organic solids, and these are some of the industrial operations where you're likely to see charging. So this range is right the way through from sieving or pouring to pneumatic transfer, where you tend to see quite a large amount of charge exchange during these collisions. So this can also be controlled and applied in processes, so such as electrostatic powder coating, nanogenerators, and one that's quite interesting given everything that's going on in the world at the moment is actually self-powered face masks, which are powered by the tribo-electrification between the layers of the masks themselves. So if we just talk through some of the mechanisms briefly, so there are 3. There's electron, ion, and material transfer. And the difference is essentially, as the name might suggest, what's being transferred in each case. So in the case of electron transfer, it's when the materials collide and an electron is transferred, and that's how charge is exchanged. In the case of ion transfer, it's where you'll have a fixed and a mobile counter ion, and the mobile counter ion is exchanged during the collision, and that's how charge is then exchanged. And in the case of material transfer, it's usually when you've got something that's quite brittle and the material itself breaks off during the collision, and then the charge is exchanged in that way. And it's sort of which mechanism is dominant is very much dependent upon the materials that are interacting with each other. So for the case of 2 metals, that would likely be dominated by electrons, whereas for a metal and an insulator, it depends on whether mobile ions are present. So if they aren't, it will likely still be electrons, whereas if they are, it will be ions. And then when you have 2 insulators, again, it's dependent upon the mobile ions. So if they're present, it'll be ion transfer. If they're both non-ionic, it will likely be material transfer. So some of the factors that influence tribo-electric charging I've just presented here, and I've tried to split them up into 4 key categories. So you've got material properties, environment, particle morphology, and mechanical force. So I'm gonna run through some of these briefly. So something I want to touch on is the work function, which is defined as a material's ability to lose an electron. And this is something that's really quite important in governing what's known as the tribo-electric series, which is essentially a list of quite a comprehensive list of materials that states how they would charge against each other. So materials at the top of the list will charge positively, whereas those at the bottom will charge negatively. And the difference between them in that list gives you an idea of the sort of magnitude that you can expect if you had these materials contacting with each other in your system. And then in terms of the environment, something that brings quite a lot of discussion in the literature is the influence of relative humidity. And so essentially, it was initially thought that just as you increase humidity, you just see a general drop off in the amount of charge transferred as the increased humidity, increased water in the air you'll get more water absorbing onto the surface of your materials, which then increases its surface conductivity, reducing your charge transfer. But some research also suggests that actually you see an increase in charge transfer with humidity up to around 30 to 40%. And it's thought that this is because the ions from the water are actually providing a source of ion transfer, which is enhancing the charge transfer. So actually up to around 30%, you see this increase. And then it's only beyond that where the increase in surface conductivity begins to almost override the ion transfer, which then leads to the decrease in charge. So that's, you know, sort of like two contrasting views on the influence of that. Particle morphology. So we've got particle size, and essentially it's that large particles charge more due to the greater area of them, but in fact, smaller particles will give you a greater specific charge due to their greater specific area. And then you have something called bipolar charging, which is actually when you could have exactly just, you know, a single component system of one material, but if you've got a different particle sizes in there, you can actually observe charging between the same materials. And this occurs essentially where you'll have large particles gaining a positive charge, whereas smaller ones are more likely to gain a negative charge. And then particle shape is essentially where, depending on the shape, it will affect whether your particles are more likely to roll, bounce, or slide. And you can imagine that if your particle is sliding, only one part of the particle will ever be in contact with the surface. So the saturation charge will be reach much more quickly, essentially, because it's only becoming charged in that one particular area. Whereas if you have a particle that rolls, the area of contact is consistently changing. So there will be the potential for a much greater buildup of charge as, you know, the surface is interacting in different areas. And then finally, the mechanical force itself. So as I was just talking about the contact area, that's something that's quite important. And then this links into the pressure and your impact velocity, because the greater the pressure, the greater your impact velocity will be. This leads to greater deformation upon contact, which increases the contact area itself, which then leads to a greater amount of charge being exchanged between the particles, or the particle and the surface. So I'll just briefly talk about powder flow properties as well, as this is something that's a little more common. So flowability, it's an umbrella term rather than an inherent specific material property. And so it can be determined and characterized in a number of different ways. So some of these include angle of repose, powder rheometers, and compressibility tests. So the macroscopic properties are controlled by the cohesiveness of the powder, which is then controlled by the van der Waals and the electrostatic interactions, which is something that I'm interested in, is linking the electrostatics and the surface charge to the powder flowability. So previous work with charge and powder flow has looked at flow rates of charged particles through a silo, trying to improve flowability with charge removal agents, and the pneumatic conveying and mixing of charged particles. But there's been a lot of observations with quite few explanations, leading to quite a clear knowledge gap. And there's no clear relationship between surface charge and the dynamic powder flow properties. So the method that we use to induce charge here at Leeds is something called charge induction via aerodynamic dispersion. So this has been developed in-house, and we use the sample dispersion unit from the Malvern G3 morphology, which you may or may not be familiar with. So essentially the material is placed within the sample well in the diagram that you see on the right-hand side, and then it's dispersed using a pressurized pulse of air. So the particles then collide with the walls of the sample dispersion unit, gaining charge, and then they drop directly into a Faraday pail, which is quite a classical way of measuring charge. And essentially it looks like, my best description is it looks like a metal bread bin inside of another metal bread bin. And then this is connected directly to an electrometer, which in our case is the Keithley 6514. And then this is where you read the charge from. So some of the advantages of this method is that it's a very small amount of powder required to give you an accurate depiction of the charge transfer. So in my case, it's usually less than 20 milligrams of powder that we use. And the sample dispersion unit itself can be very easily varied. So you can test your sample against a variety of different metals and polymers. So just off the top of my head, we have steel, copper, aluminium, brass, PTFE. And due to the nature of this method, with the particles dropping directly into the Faraday pail, this should mean that there's no charge leakage, as the charge on the particles can be measured immediately after dispersion. So for our powder flow properties, we use an FT4 powder rheometer, And this characterizes the powder flow resistance by determining the flow energy required to drive the impeller through the powder bed. And it's very accurate in dynamic conditions. So you can allow for differentiation between similar materials, which is quite useful when we're looking at different surface modifications of glass beads. And for the purpose of this test, the samples have been tested in both confined and unconfined conditions, which essentially just means that the blade moves downwards and then moves back up, and we've characterized the energy required to drive through the bed in both conditions. So just a bit of background on the surface modifications that we did. So we did the acid washing of the glass beads in something called peroxymonosulfuric acid, which is more commonly referred to as piranha solution. And it's a combination of sulfuric acid and hydrogen peroxide. So essentially, this allows us to ensure that there's no organic residue left remaining on the surface of the glass beads as they're oxidized to CO2. And it leaves the OH groups exposed upon the surface following on from the treatment and makes the surface extremely hydrophilic. So then we took these acids, so we left a sample of acid wash glass beads, and then we took these and we silanized them using something called Sigma-Coat, which is a chlorinated organopolisiloxane. And for anyone interested in the structural formula of that, it's here. And this essentially, as opposed to the acid washing, leaving them hydrophilic, this silanization makes the material surface extremely hydrophobic. So onto the results from the FT4 powderiometer. So we have both the unwashed and the silanized. Unfortunately, we've not yet been able to accurately characterize the acid wash glass beads. We've seen quite a lot of variation in these. So we're not too sure quite yet what's going on there, but we're looking at doing some different techniques such as AFM and XPS to try and get an idea of what's going on the surface to see, what's happening with the acid wash glass beads and why we're getting such variation in the powder flowability tests. But you can see with the unwashed and the silanized glass beads, there's a dramatic increase in the energy required to drive the impeller through the bed when you've surface modified these particles with the Sigma-Coat solution. So following on from that, we did the Tribo charging test. And what we can see from this, so this was with the stainless steel SDU at a 1 barge inlet at around 60-ish% humidity. And from this, we can see that both the acid, so all of these particles charge negatively, but what we can see is that both the acid washed and the silanized particles charge significantly more than the unwashed counterparts. And this likely goes some way to explain why the silanized particles are so much more cohesive than the unwashed, because they're charging so much more during the aerodynamic dispersion, which means that they're almost guaranteed to, when you're driving a metal impeller through the bed, you're also going to see a significant amount of charge build up there. But something else interesting that we noted was that quite consistently with all the samples, as you're increasing your sample volume and your number of particles, the actual specific charge, so this is your charge per unit mass, is actually decreasing as the volume is increased. So we had a little think about this and we decided to run some simulations. So we used CFD coupled with DEM, so that was to try and model the dispersion of the particles through the powder bed, the dispersion of particles using the aerodynamic dispersion. And what we observed was actually that essentially, so with the 5mm cubed and the 13mm cubed samples that we've been using, when you look at the 5mm cubed over the duration of the 20 millisecond pressure pulse, by the end of it, you can see that actually the average number of particle wall collisions is quite significantly higher for the 5mm cubed than the 13. It's about a 10% difference. So it looks to be about 17 particle collisions by the end for the 5, whereas it's only around 15 for the 13mm cube. So whilst this goes some way to describing why we may be seeing significantly lower charge or significantly lower specific charge in the higher volumes, we thought we'll have there's more to be looked at here. So we started thinking about the average particle velocity. And you can see that for the 5mm cube again, quite consistently, you're looking at higher average particle velocities, particularly in the first millisecond of the simulations. Now, this may not seem too consequential, but actually, so some previous work has been done with these simulations where it was modeled using laminar flow. And this was done by Francesco Alfano in Italy. And what they observed was that in the first millisecond, this is where you see the majority of the charge buildup. So when you combine that with the fact that in our first millisecond, you're seeing this greater average particle velocity, And then the fact that there's these greater number of collisions occurring at the lower particle volumes, it begins to paint the picture of why we're seeing this higher specific charge at lower volumes with less particles compared to the lower specific charge with more particles. And then just to kind of round up this tribocharging analysis, we also considered the influence of humidity. So this is with the unwashed glass beads only, with a 1 barge inlet against a stainless steel SDU. And you can see that with these tests at 38% and 62% humidity, you can see a dramatic change in the amount of charge that's being transferred between the materials. So, at the 62%, it's significantly lower than the 38%. But we really need to test this relationship with both the hydrophobic and the hydrophilic material, so the solenoids and the acid wash glass beads, because it'll be interesting to see whether how hydrophobic or hydrophilic material influences how sensitive they are to changes in humidity. And then what we really want to do is examine this 20 to 40% humidity range that I briefly referred to earlier when I was discussing about the effects of humidity. So we can see if we can, because with our method, with the lack of charge leakage that we expect to see, we really want to see if we can observe the effects of ion transfer, or whether we just see a straight decrease in the charge transfer as humidity increases. So just to conclude this talk, these glass Ballardini powders that we've been working with, they've been observed to become significantly more cohesive when solenoized with sigma coke solution. And then both the acid washed and solenoized glass beads charge much more strongly than their unwashed counterparts. And just to confirm, as has already been known, really, the influence of humidity is significant in the transfer of charge. So thank you for listening, and I'd be happy to take any questions now.